Stock market analysts are constantly searching for ways to exceed the kinds of return they can get with just a buy and hold of stocks, indexes, or ETFs. There are three types of analysts: the technical analysts who look at price changes, patterns, things like that in the activity; fundamentalists who look at the strength or weakness of a company or industry; and sentimental analysts who look at the attitudes of investors. Oftentimes, they're looking at from a contrarian perspective, assuming that investors are wrong. Now, all of these factors can influence the price of a stock over time, but there are also exogenous or external factors that can influence stock prices, and those include things like news headlines, which convey confidence or lack thereof in individual companies or industries or markets as a whole. Now, for this project, we're looking at news headlines and attempting to classify them as very negative, negative, neutral, positive, or very positive. In order to classify those headlines, we're using data that has a rating from 1 to 5, 1 being very negative, 5 being very positive. There are two models used in this study. The first is a naive Bayes model using the multinomial NB class from scikit-learn, and it's vectorized on the term frequency inverse document frequency, or TF-IDF vectorizer. The second model uses BERT. It uses a pre-trained model called TF Auto Model for Sequence Classification, and it uses a checkpoint named BERT base uncased. The tokenizer is, of course, the one that's trained for that model as well. The data comes from Kaggle. The link is here. The files, there are 3 of them, contain headlines and sentiment, and you can see there's also a date in this format, and that is something that I'd like to use at some point for really verifying the sentiment. We'll talk more about that as we go forward. Again, the sentiment values or tags are 1 through 5. We're only going to use 2 of the 3 files. I found some issues parsing data in one of them, and it was fairly small to begin with. The files are not huge. They're 1.5 meg to almost 3 meg, and they'll be available with the project. The composition of the data is interesting, particularly because it's so unbalanced. There are almost 30,000 very negative ratings and 10,000 very positive ratings. So that's the majority of the data, almost 80%. On the right-hand side, you'll see something called class weight for training. This is something that I experimented with and ultimately left in to use to influence the training when calling fit, and I'll talk about that later. For testing and training, the split is essentially 80-20. So we're using 80% of the data for training and validation and 20% for test. And then that is broken down further on the BERT model. I initially started this project working with Windows native. I have a GPU and it's worked fairly well, but you have to use TensorFlow 2.10 to make that work. And the libraries that ultimately had to be pulled in for BERT did not work with that. A lot of incompatibilities. I ended up falling back to running it on Colab. It's fairly straightforward. You upload the notebook and update the data files. Put the data files in a directory called data under your Colab folder. And as you'll see below, I've got the code that's required. It's in the notebook that recognizes that we're running on Colab and points to the right folder and mounts it for Colab. There are also some cells near the top of the notebook I'm not going to talk about here that have global settings to tune the models and to control verbosity. Learned quite a bit along the way here. A lot of it had to do with getting the Keras version of the BERT model working. And I'll talk about a number of areas that I ran into, and hopefully that will provide some useful information. The first, of course, was tokenizing. I tried to pass the data series from the data frame directly to the tokenizer, and it was not happy with me. I got a lot of errors. So I ended up having to pass it as a list, simply convert it to a list with the list function. The output structure of the tokenizer is interesting. It's not just a list. It is, in fact, an object, and it has multiple lists inside of it. One of those lists is the inputs, and it's tokens, but it also has a start and stop token, 101 and 102 in my case. The output also has a pre-computed attention mask called attention mask. And so as a result, you tokenize, you get your attention mask, it's included in the object, and you can simply pass that to the train or the fit rather, or the evaluate functions. The one thing I did have to do though was to convert it to a dictionary after the conversion. So I would recommend that you tokenize separately. So because the structure is fairly complicated, but I found that I had to pre-compute the maximum length and a couple of other things that we'll see on the next slide. So the really important thing is that there's a parameter called padding. And if you set that padding parameter to true, it apparently overrides the maximum length that you provide. So if you think about it, your different splits may have different sequence lengths or different sentence lengths in this case. And the tokenizer doesn't know that. So you presumably pass it a max length and it honors it. But if you set padding to true, it's not going to honor it. And I found that I had to set it to literally max underbar length. And in that case, it would honor the maximum length and all of the dimensions of the outputs matched up. Took a little digging, needless to say. A second area was to categorical. Initially, I was using to categorical to pre-process the input. Whether that's an error or not required, I can't say for sure, but I ended up just passing the raw values and it was quite happy with those. The output of the model, the output from predict is actually not, it's not probabilities, as you might expect, it's logits. And you have to convert those logits by using argmax. Some documentation I found recommended using softmax. Others just said, no, go ahead and use argmax because the values are actually sufficient to figure out which one is the best. When I started to train the model, I found that all the layers were frozen, and I initially thought that I was going to unfreeze the classifier and the dropout layers. And you'll see the layers on the next slide, but I found that I needed to really enable training for the base layer. And it was recommended that you train the whole model with a very small learning rate. And I found that it did seem to converge a little faster and on a higher accuracy during training when I did that. I've got code in there that allows you to flip back and forth if you want to play with this. So you can train just the classifier and dropout layers, or you can train the base model itself. So if you look at the model with a summary report, you see that there are three layers. There's the main layer that has a meager 109 million parameters. And then the classifier has 3,800 roughly. If you train all of them, you're going to be training your 109 million plus. If you train just the dropout and classifier, you're going to be training only 3,845. The class weights that I talked about before are calculated for each label, and they're passed into the fit function. And their purpose is to influence the loss calculation, and the attempt is to undo or mitigate the imbalance that's there. And you can see from the values at the bottom of the screen that the greatest punishment or penalty was really on class 0, which is the shifted very negative rating. The code is here that's used to calculate the weights from scikit-learn, and you do have to create a dictionary after generating the vector. And you can see the dictionary at the bottom shows a mapping from label to the weight. You simply pass that weight to the fit function as class weight. The results were a little bit surprising. In the naive Bayesian, I wasn't surprised to see how much weighting went to the very negative predictions. But in BERT, despite a number of different combinations of learning rates and of epochs, the training only slowly started to converge. I was hoping to see a nice diagonal, but did not. It's certainly much better than it was in some of the early testing I did. Again, this is testing the entire, this training the entire model, I should say. The classification report actually showed the naive Bayes doing a better job by far than the BERT model. And that is, I think, is affected by the fact that, and you can see the recall score for very negative is 98.98. And I think that's a factor of how many misclassifications were actually there. And it really was confusing as to why that was different. I'll talk about that in a minute. The training and validation and testing numbers did not match up with the classification report. And in fact, they showed a training accuracy of over 99%, a validation accuracy of 78%, and a testing accuracy of 75%. So I would have expected better results on the classification report. Doing some digging, I found that the discrepancy between the BERT training and the classification report is that the BERT training, the Keras training of the Keras model, is in fact using categorical accuracy based on categorical cross entropy. The classification report is using binary accuracy, and the calculations are definitely different. So there is an explanation. I don't have the full details on it yet. With fewer epochs and higher learning rates, the BERT model confusion matrix really ended up looking more like the naive Bayes. I don't have a slide for that. Learning definitely seems to be a factor. And for the hours and hours that I trained this with different combinations, it certainly seems like if you could train it long enough, you could get a good result. Early stopping kicked in fairly often, and I had to increase the patience on early stopping quite a bit. The interesting thing is that the same model, I used it on a different homework assignment, produced much better testing results. So I took a step back and began to look at the data. And one of the first things I found is that reading through even an intuitive analysis of the data, if I were to create a rating for it, it would not have been the rating that I saw. And I have just a few examples here. There are more in the appendix of the report. But things like saying the recovery is a long way off and we need more fiscal help, I don't know how that gets a 5 rating, but it did. On the other hand, when the SoftBank shares returned to a .com bubble era high, they got a 1 rating. It does seem like the verbiage is a factor in the context, which I'll talk about in a bit. Digging a little bit deeper, I found that in fact the data was created using a BERT model a different checkpoint. It was the one you see on the slide, NLP Town BERT-based multilingual uncased sentiment. There was no validation done. The text was fed through, the sentiments were generated, and the data was saved. And I thought it was kind of interesting that BERT couldn't track back its own data, but I think given the weakness of the assignments, I suspect that's part of it, and I'll come back to that. So there are three basic conclusions that I drew from this experience. The first is that you can code, you can debug, you can review the data outputs, but it's critical to understand your data set or sets. And having lots of data is good, but having lots of good and proven data is better. And I don't feel that this data set was well proven. If you're going to use BERT to generate sentiment, it's important to validate and round trip the data. You want to make sure that you can generate the same sentiment again. A single pass through the code that I saw, and I waited to look at the code. I wanted to get my own model written, but the code really didn't do much testing or validation. And finally, BERT is a powerful model, but context is lacking with these headlines. I found myself mentally reaching for external rules of thumb, for example, when determining whether something like layoff is a good thing. Sometimes it would be rated good, sometimes it would be rated bad. From experience, I believe layoffs are generally considered good for a company's stock. This leads to a lot of potential future work. For example, looking at stock market data as a benchmark for classifications, tuning the network to recognize classifications that are not borne out by price movement or payment of dividends for that matter. And some possibilities include looking at the company, looking at the country, adding the ability to classify a headline as not classifiable, whether that's removed from the data or kept as a separate category. I tend not to like losing data, so I would tend to think we'd want to keep it as a classification. I would also like to consider how named entity recognition could improve providing context for headlines. I'm not really sure how I would merge in stock prices for specific companies, but I think it's possible that a network could be trained to learn to learn and integrate that data. A lot of references here. I recommend looking at them, particularly the deep learning one toward the bottom.